Hello, in this video, I'm going to talk about the MBIS charge partitioning scheme, or the minimal basis iterative stockholder atomic charge partitioning scheme. So what is charge partitioning? Basically, electrons spend more time around one atom compared to other atoms and molecules when they have differing atoms. And this is called electronegativity, which describes how much an atom favors electrons compared to other atoms. And charge partitioning is a scheme that assigns electrons to atoms in a molecule based on the average number of electrons that are around that atom. And we can calculate an atom's charge based on the difference between an atom's nuclear charge and the number of electrons assigned to the atom. So an example is water, where the charge partitioning scheme may assign 8.8 electrons to the oxygen and 0.6 electrons each to the hydrogens. So the charge on the atomic charge of the oxygen will just be 8 minus 8.8, or negative 0.8. And the atomic charge of the hydrogen will be 1 minus 0.6, or positive 0.4. You may have learned in general chemistry that atoms or molecules like water have something called a partial charge, and a charge partitioning scheme is a way to quantify the partial charge that an atom has. MBIS is a particular charge partitioning scheme that is mathematically simple and is derived by Thun-Verstraelen in the paper Minimal Basis Iterative Stockholder, Atoms and Molecules for Force Field Development in 2016. This paper could be found in JCTC, or the Journal of Chemical Theory and Computation. I will not go over the theory and derivation much in this video, as this video is just an intro, but basically how this is all derived is based on the concept of information loss, as described in the equation here, where rho A is the atomic density and rho A naught is the proatomic density. The proatomic density is basically an atom's electron density at a point, as if the atom was isolated and not part of a molecule. Now, the condition to satisfy is that the sum over all the atoms of the atom's electron density has to equal the molecular density, or basically the electron density of a molecule at a point in space. And because of this constraint, we could write a Lagrangian that takes into account the information loss and the fact that the sum of atomic densities has to equal the molecular density. So when we minimize this Lagrangian, we get this equation, which is called the Hirschfeld-Stockholder partitioning equation, which basically says that atomic density of an atom equals the molecular density times the proatomic density divided by the promolecular density, which is basically the sum of all atoms of the proatomic density. In the MBIS charge partitioning scheme, the proatomic density is defined as the sum over all the shells of an atom of rho AI naught, or we can call it the proatom shell density in this case, or the electron density in a shell of atom A. Now, the number of shells an atom has is based on its rho in the periodic table. So hydrogen and helium would each have one shell, and lithium through neon would have 2 shells, and sodium to argon would each have 3 shells, etc., and so on. Now the proatomic shell density in MBIS is defined as by the following equation: NAI divided by sigma AI cubed 8 pi times the exponential times e to the negative r minus RA over sigma AI, where r minus RA absolute value is the distance of a point in space to the nucleus of an atom. Now, NAI is defined as the number of electrons in the shell, and sigma AI is called the shell width. In MBIS, NAI and sigma AI are optimized in an algorithm in order to find the number of electrons assigned to an atom. Another constraint we can introduce in MBIS is the fact that the sum over all space of the proatomic density has to equal the sum over all space of the atomic density. Basically, it says that the number of electrons in an atom, no matter whether you calculate it as a proatom or an atom in a molecule, they're equal. And because we are still minimizing information loss, we can introduce another constraint into this Lagrangian. And through this process, we will get a set of equations. We would get a set of equations describing NAI and sigma AI in terms of the rho r, the molecular density, rho AI naught, the proatomic shell density over rho naught, the promolecular density, and sigma AI in terms of the same things, except that it's multiplied, except that atomic distance, except that electron's distance to the atom's nucleus is a factor. So now we have these sets of 4 equations that can be used to generate a self-consistent algorithm, which I will describe on the next page. So here's how the MBIS algorithm goes. You make an initial guess of NAI and sigma AI, and then you use that to approximate rho AI naught, rho A naught, and rho naught. And also you need rho R, or the molecular density, and that is calculated using quantum mechanics. And if there's convergence, you end the process. If not, you use the values you calculated for rho AI naught, rho A naught, rho naught to update NAI and sigma AI, and the cycle continues. Now the criteria of convergence is based on the difference of the pro-atomic densities over all atoms. For all atoms. And basically the algorithm is considered converged if the maximum of all of the atomic integrals is less than 10 to the negative 8, or the square root of that. And in the size MBIS algorithm, you can actually set the convergence criteria, but the default will be 10 to the negative 8. And I realized that I made a typo, or a Rido, in the convergence criteria equation, so let me correct that real quick. All right, now I've corrected it. It should be to the positive 1/2 power, not negative 1/2 power. Sorry about that. But anyways, after convergence, the atomic charges and multipoles can be calculated using the atomic densities derived using this algorithm. All right, next I will show you, in the next video, I'll show you how to use Psi4 to calculate an atom's MBIS charges, or molecules' MBIS charges.